Okay, so I'm happy to have the chance to introduce Pierfrancesco Guarino from the University of Udine. He's a very broad interest in foundations of game theory, particularly epistemic game theories, what people believe, what they believe, and so on. And we will see a lot of that today. So, Pierfrancesco, the floor is yours.
Merci. Tout d'abord, je voudrais remercier Olivier, qui n'est pas ici, Stefano pour l'invitation, pour l'organisation et en général pour l'opportunité de donner ces conférences. C'est un honneur et en fait, c'est toujours un plaisir de profiter de l'hospitalité de l'institution. J'avais pensé de donner ces conférences en français, mais après un petit moment de réflexion, compte tenu de mon français, je pensais que c'était la meilleure façon pour ne montrer pas ma gratitude. Donc, je commencerai à parler anglais maintenant. Yeah, oui, c'est mieux. By the way, yes, as Miki pointed out, I'm the one on the left, if this is going to work at some point. This is joint work with Gabriel Ziegler from the University of Edinburgh, even if Gabriel is going to formally move to the Freie Universität Berlin from the very 1st of October. And, well, as usual, we have a huge amount of ground to cover, so let's crack on. Let's turn and burn. This is the outline of the presentation for today. So we will start by getting some intuition behind what misalignment is all about, the misalignment we want to capture in the title, okay? And then we will have to introduce some much-needed background knowledge that we will exploit to define misalignment. Now, if we stop for a second and we think about the way in which we typically use the verb to capture in science, it is as a synonym of the verb pretty much to define. It turns out, though, that here we are going to use the verb to capture in a very literal sense, in the sense of, getting a grip on something. So we will get a grip on misalignment by introducing a framework to capture it, okay? And then I'll show you, and hopefully I will convince you that misalignment matters. So what does that mean? For us as economists, that means that misalignment, well, contemplating the presence of misalignment in our analysis leads to novel behavior predictions, which is crucial for us as economists, okay? So intuition. So everything starts, funnily enough, from a grocery store. So I think I can safely bet that I can leave this room, get to the first grocery store right down the road, pick a random customer, tell to that customer what I'm going to tell you right now, and that person is going to understand everything to a T. Which, in this day and age of science, is somewhat surprising, because we live in a world in which it is very difficult even to explain to our colleagues what we are doing, right? So, is it really possible? Okay, let's see. Well, first of all, this is what I would describe to the random customer, okay? So let's take the perspective, okay, of a know-it-all chap. There is a know-it-all chap, okay? And then there are a bunch of people. Now, this bunch of people have beliefs regarding something such as the weather in Paris tomorrow. Fingers crossed it's going to be sunny, okay? And all these beliefs are going to be known by the know-it-all chap. Well, needless to say, right? That's not enough, though, because this bunch of people also have beliefs regarding each other's beliefs regarding the weather in Paris tomorrow. They also have beliefs regarding each other's beliefs about the weather in Paris tomorrow, and so on and so forth. We call them higher order beliefs. Now, and this is all known, this tower of beliefs are all known by the know-it-all chap. So we have misalignment if there exists at least one person that has beliefs regarding the beliefs of another person or the higher order beliefs of another person that are flat out wrong. And now, I think that in the grocery store, somebody would go like, okay, wait a second, it's a little bit cumbersome. So, okay, you have all this kind of stuff, and you have misalignment, okay, when you have one person that basically is wrong about the beliefs, or what you call higher order beliefs, of another person. What's so special about this? This happens all the time. This is life, right? Well, funnily enough, this happens all the time, but we never contemplated this in econ. Never. okay? And it turns out, and if somebody now is thinking like, well, it's not that we never contemplated it. It's that it doesn't lead to novel behavior predictions. So we don't care, we are economists. Well, once more, I hope I will convince you that this leads to novel behavior predictions. Now, this is the grocery store version. Let's come back from the grocery store. No grocery store, by the way, is supporting this research. And let me just now give you a little bit of a definition, still informal, of the social scientific phenomenon we are interested in. And I know it sounds very grandiose, but yeah, we are interested in a social scientific phenomenon that, and this is literally the opening sentence of our paper, has never been identified before. Hence, a fortiori, we never got the corresponding behavior predictions. And we call this new phenomenon misalignment. This is the informal definition, okay? So take the perspective of an outside omniscient observer. Misalignment arises whenever, given a set of agents that have beliefs regarding something, and higher order beliefs, okay, and mutual and higher order beliefs, well, once more, misalignment arises if there is an agent that has beliefs regarding the beliefs of another agent or the higher order beliefs of another agent that this latter agent does not actually hold. Once more, it's cumbersome, but very soon I'll give you an example, and I think that you will see and you will agree with me that this happens all the time. It's literally life, okay? Before getting there, let me address some points, okay? Because what we want to do in this paper, once more, is to capture this, okay? First of all, let's identify some properties. And these are 3 properties we identify. First one, we need an interactive environment. We need multiple agents. We need multiple chaps. Second one, it arises out of hierarchies of beliefs. As Michi pointed out, what I do very often is about beliefs and beliefs about beliefs and beliefs about blah, 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 blah. And I think I used the word belief like 50 times in the last 5 minutes, okay? So yeah, it's about hierarchies of beliefs. It turns out that, and rather crucially, this is elicitable. Because it's about hierarchies of beliefs. We can elicit hierarchies of beliefs. As economists, we do not ask. We observe, we elicit, we don't ask. This is something that can be elicited. So thumbs up. There is behavioral content here. We can get behavioral information. By the way, if somebody is feeling a little bit uncomfortable with this word here, this outside omniscient observer that in the grocery store was the know-it-all chap, well, in my opinion, you should not. And the reason is the following. Taking the perspective of an outside omniscient observer is something that we do literally all the time in science. And also in econ. The only difference between this paper and other works is that we are very, very explicit. We are adamant on the point, and we go like, take this perspective, okay? We are taking this perspective. We want to let you know this very clearly, okay? Now, so this is, once more, grandiose statement. This is the phenomenon we are interested in. Now, the problem is, how do we tackle it in this paper, in this project? And this is the path we pick. Okay, so once more, this is going to be informal, okay? And it goes as follows. Once more, taking the perspective of an outside omniscient observer, this is the still informal definition. Let's read it together. So, given a set of agents, a domain of uncertainty, and a modal of the interactive beliefs, okay, the modal presents misalignment if there exists an agent I that holds beliefs regarding an agent J's beliefs or higher order that are not actually held by J. So how do we plan to capture misalignment in this work? By identifying misalignment as a property of the modal of the interactive beliefs, as a property of the state space. That's the plan for today. Now, I'll give you an example to feed our intuition. And this is going to be the running example. Well, this is the running example in the paper, and it's going to be our running example in this presentation. It's a very simple one, okay? Consider 2 agents. We have Anne and Bob, and they have beliefs regarding the weather in Paris tomorrow, okay? And we assume the following as outside omniscient observers. And by the way, when I say that we assume this as outside omniscient observers, you pick the interpretation you want. There are 2 options. Roughly. First option is you're simply assuming this. You're assuming this kind of knowledge concerning the hierarchies of Anne and Bob, Or another one, which fits very much what happens in the lab, in experimental econ, you elicit these beliefs. So you know them. You know them in the sense that you elicited, and you can go like, yeah, this is literally what they have. Or once more, you can assume. You pick the interpretation. It doesn't really matter, the interpretation. So once more, let's assume that we as outside omniscient observers, we know the following, okay? We know that unbeliefs, and by the way, whenever I use the verb to believe, I use it as a synonym of putting probability 1 on an event. This is in the spirit of Jimmy Savage, The Foundation of Statistics, 1954, okay? It's completely standard. So unbeliefs the following. First, and first here means first order belief. We will see that this is very technical, okay? But for the time being, we can, describe everything in plain English. First order belief, she believes that it is going to rain in Paris tomorrow. Fair enough. Now, second order belief, she believes that it is going to rain in Paris tomorrow and that Bob believes the same. So a second order beliefs contains, this part here, contains the first order belief, but then there is an additional part which is about Bob. And this is the crucial part. So she believes that Bob believes it is going to rain. Now, if we would move to the third order belief of Anne, we would get that she believes it's going to rain, that Bob believes that it is going to rain, and that Bob believes that she believes it's going to rain, and so on and so forth. So for Anne, it's all about rain in Paris tomorrow. It turns out, though, that we know the following. We know that if we look at Bob beliefs, well, Bob believes, first order belief, that it is not going to rain in Paris tomorrow. And now if we also go for the second, he believes that it is not going to rain in Paris tomorrow, and that Anne believes that it is not going to rain in Paris tomorrow. If we go to the third, Bob believes that it is not going to rain in Paris tomorrow, that Anne believes that it is not going to rain in Paris tomorrow, and that Anne believes that he believes that it is not going to rain in Paris tomorrow. So for Bob, it's all about not raining. So when do we have misalignment? Here it really doesn't matter which agent you pick, but we will always focus on Anne in this presentation. You see, we have misalignment. Why? Look at Anne's second order belief and focus on this part. She believes that Bob believes it is going to rain. But now look here. We know this is not true. Anne is wrong. Her belief about Bob, as I said in the grocery store, it's flat out wrong. Bob believes it is not going to rain. That's misalignment. This is what misalignment is all about. And as you can see, this happens all the time in life. So yeah, I think it would be important, we think, with Gabriel, that it would be important to get what are the behavioral predictions that we obtain when we contemplate such a ubiquitous, this is literally the word we use in the opening sentence of the paper, such a ubiquitous phenomenon, okay? So what's then the plan for today? That's the plan for today. First of all, we're going to check if type structures a la Arsani capture misalignment. So type structures a la Arsani are one way, like the standard way to capture hierarchies of beliefs. It's a Nobel Prize winning idea, 1994, John Arsani, and we will talk very soon about this, okay? Huge spoiler, they don't. Otherwise there would be no paper and no presentation. They don't, okay? It turns out that then we will use all this kind of stuff here to move from the informal definitions I gave you before, and I hope that we all agree on the fact that what I told you in the grocery store, the grandiose social scientific definition, and the informal one that we want to capture in this very paper, they are all literally three sides of the same object, okay? It's all the same, really. I was just changing words, okay? So now we will move to a formal definition. And then what we are planning to do is to get like operational implications from this definition. If that sounds a little bit mysterious, I'll show you what that means. And finally, since we have a problem here and type structures that are Arsani fail, we are planning to develop a framework to identify behavioral predictions under misalignment, okay? That's the plan for today. So everything starts from background knowledge. We need, full disclosure, biggest problem in presenting this paper is that we have to see how the machinery, the standard machinery in game theory, in micro theory, in economic theory at large works, to see where it fails. So we have to revise it. That's what is going to happen here. We are going to see how it works with Arsani, how literally Arsani type structures work. Because then, once we see how they work, we will see why they fail. And so a huge part, in a sense, of the presentation, not huge, but yeah, I mean, part of this presentation is really about revising things we know to see, that's how it works, that's why it fails. And this is what's going to happen now, okay? So everything starts from infinite coherent hierarchies of beliefs. This completely infamous exotic / exoteric / mysterious concept that hopefully we will demystify. So we fix a set of agents. Capital I stands for individuals or agents or players. In this context, it's not a game. We call them individuals, A and B, Anne and Bob. We have a common domain of uncertainty, theta, which we also call set of states of nature. And this is a way of capturing our example. Theta R, yes, it's going to rain. Theta N, no, it's not going to rain. Okay, let's start. This is a first order belief of N. Okay, the notation in this paper is completely standard, but just to clarify, capital delta of theta is the set of all probability measures. So what is a first order belief for N? We put number 1 to say that it's a first order, right? We put A to see that it's N. And first order belief means what? It means that, for example, this is one possible first order belief for N. She puts probability a half on the fact that it's going to rain and probability a half on the fact that it is not going to rain. In our example, the one I told you before, our running example, she's going to put probability 1 on the fact that it is going to rain. But this object here, it contains every possible belief of that kind of form. Now, for Bob, it's the same. They're just changing from A to B. But it's pretty much the same. Let's put some colors. They are going to be useful. No. This is just to simplify the exposition. No, not at all, actually. We go like topologically with compact spaces. You will see very soon, but it's just to feed the intuition. And this is going to be, in general, the running example, but I'm introducing infinite coherent hierarchies of beliefs, just in this case, because it's going to be useful for the rest of the presentation. So let's put some colors, okay? Why are they useful? Because when we move to second order beliefs of N, okay, we put a number 2 here because it's a second order belief. We put A because it's for N. Look, now this object is what? It's a probability measure over theta, the original domain of uncertainty, the set of states of nature, and Bob's first order beliefs. And I think the colors make this pretty obvious. You see, the blue one, original domain of uncertainty. Red one, Bob's first order beliefs. So now if we move to Bob, new colors, we have that Bob second order belief is about what? The original domain of uncertainty, red one, and Ann's first order beliefs. And if you think about the way in which I was describing in plain English Ann's first order belief, it always contained, second order belief, it always contained the first order belief. The second order belief of Anne in our example is she believes it's going to rain, she puts probability 1 on the fact that it's going to rain, and she believes that Bob believes it's going to rain, and so on and so forth. Now, third order belief, it's even more cumbersome. It's a probability measure, all this kind of stuff. And let's see. It's a probability measure over what? The original domain of uncertainty, blue one. Bob's first order belief, red one. And now all this stuff is Bob's second order belief. And we can go on forever and ever. After all, they are infinite, okay? Now, why are they called coherent? Because they satisfy this property. Okay, what does that mean? It means basically the following. Let's focus on this case here, and I will give you also the economic intuition. The reason why this infinite hierarchies of belief satisfies this coherency requirement is, in a sense, mathematical. It's due to what is called Kolmogorov extension theorem, but we want to get some economic intuition. I'll give it to you. Let's now focus on what this means. Let's focus on second order belief of N. What we want is that when we take the marginal over the relevant domain of uncertainty for the first order belief theta, the two have to be one and the same. And what is happening is that basically, second order belief, when you take the marginal over here, it has to be equal to this. And think about the following. It's very natural. It's a very natural coherency requirement. Imagine that we are in the lab, okay? We elicit Anne's first order belief. And she goes like, I believe it's going to rain. Okay, thumbs up. Now she doesn't get any new piece of information. We elicit her second order belief, and she goes like, well, as a matter of fact, I believe it's not going to rain and whatever about Bob. We would be a little bit puzzled, because according to the Bayesian paradigm, she doesn't have anything to revise her beliefs, but they're different. Her first order belief was, I believe it's going to rain. Her second order belief is, I believe it is not going to rain and whatever about Bob. So what we want to have is that when we go for the second order belief, she's going to be consistent with what we had before. As a matter of fact, when we go to the third order belief and we take the relevant part for the second order belief, they have to be the same, and so on and so forth. This is the coherency requirement. Once more, it's very natural. In the spirit of the Bayesian paradigm, she shouldn't revise her beliefs. Now, if she doesn't get any new piece of information, okay? So, this is one reason why we call them infinite coherent hierarchies of beliefs. There is an additional reason, which is this one. At every step, every agent has to put probability 1 on the fact that the lower beliefs of the other agents are coherent. Once we have all this kind of stuff, we get the answer to something that I truly find like very beautiful, honestly. What is a type in the sense of Arsani? I always say this to the students. Game theory 101, right? We start game theory, we get introduced, we get exposed to games with incomplete information, and then we find this notion of type. And a student, maybe there is some brave student that goes like, what is a type actually? And typically students don't do it, okay? As a student, I didn't do it, but I had no clue what a type was, okay? It turns out that if somebody asks, the answer is, well, it is a self-referential object, which of course is not going to help the student at all. But what is then a type for Arsani? This is literally the answer for game theory 101. A type is an infinite hierarchy of coherent beliefs. This is what a type is. This is the genius of Arsani. A type is literally one object, okay, for the agent I, that captures this sequence of probability measures that goes to infinity, okay? And it turns out that, I like to use this expression, it's a little bit, like, if you think about the Lord of the Rings, in the Lord of the Rings, there is, the one ring, right? The one ring to rule them all. A type is one probability measure to rule them all. That's what a type is, literally, okay? So I think it's a good way to remember it. It turns out that here we use this notation that we're going to employ a lot. So capital T1 of I is the first order universal type space of agent I. When we put this object together with this object, we get the second order universal type space of agent I, and so on and so forth. So this is the informal description. Terribly cumbersome, okay? This is the formal description, which is even worse. But we need this. I typically say when I put something like this that the gods of mathematics begged me to put it, but we will breeze through it because we get the intuition. We just need literally this page to fix on some notation. You see, these objects here are the ones I just showed you before. Here there is the coherency requirement. This is what is called a recursive definition, compact set, okay? So it's fine. States of nature, once more, theta is going to be the states of nature, the set of states of nature. We get capital T of star, it's the universal type space of agent I. Notice, is nothing more than a Cartesian product with this little arrow here is an inverse limit, but we don't care about that. It just means that we're not really taking the Cartesian product, we are just taking the subset of the Cartesian product that satisfies the coherency requirement. And then we have the universal type spaces, capital T star, which is the Cartesian product of the universal type spaces of every agent. And finally, universal state space, capital omega star, which is Cartesian product of set of states of nature and the universal type space. Now, let me drop this bomb right away and then we forget it. Turns out that Martin-Zamir in 1985, along with other people such as Armbruster Sternberg in 1979, Brandenburger and Degel in 1993, Heifetz 1993, and so on and so forth, they show that there is like a nomomorphism. What is a nomomorphism? It basically means that what we have here is equivalent, in a very technical sense, to what we have here. What that means is, strictly speaking, homomorphism means that they are topologically equivalent. They're equivalent up to continuous transformation. But for us, these details are irrelevant. What it means is that the universal type space of agent I, this set of all infinite coherent hierarchies of beliefs, is nothing more than the set of all probability measures over the original states of nature and the types as infinite coherent hierarchies of beliefs of the other agents. And by the way, whenever I use in this presentation the word type, I use it as a synonym of the word infinite coherent hierarchy of beliefs, okay? Now, it turns out, why is this stuff called universal? There is a technical sense. We're not getting into these details. What we care about is that this object is huge. So given a set of agents and a domain of uncertainty, This is the largest possible object, without redundancies, that contains every possible hierarchy of beliefs of these agents regarding the original states of nature and each other's beliefs and so on and so forth. It's humongous. Everything is there. Nothing is missing. Okay? Now, turns out that we call the resulting object, when you put all these things together and we plug it in this tuple, we call the resulting object the canonic hierarchical type structure. Why is it hierarchical? Because we built hierarchies. We built the hierarchies from the ground up and we got this object here, okay? We're going to use very soon this little piece of notation, okay? We had this beta function, just a second, Michi. We had this beta star function, this homomorphism. We take the tau star, which is nothing more than a way, this means that we're taking the marginal over this probability measure, that is over this object here, just for the types. And it's just a way of saying, look, pick an agent, pick a type. With the tau star function, we just care about the beliefs of the type of that agent regarding the types of the other agents. Okay, so yeah, we have this tau star function. Now, this is the so-called explicit way of capturing infinite hierarchies of beliefs, okay? And it's terribly cumbersome, but it is somewhat intuitive in the sense that we are building from the ground up, okay, with all this kind of machinery, what we were saying before. And at the end of the day, we get this humongous object, okay? It turns out that Arsani found what is called the implicit way. And that was with type structures, okay? And this is the definition of type structure introduced by Arsani in 1967-68. This is a Nobel Prize winning idea. He won the Nobel Prize in 1994 for this trilogy of papers on management science. And this object here is a way of capturing infinite coherent hierarchies of beliefs in an implicit way, okay? Now, this is very similar object to the one I showed you before with some small differences, such as, for example, the fact that this is just continuous. It's not an homomorphism, but let's not get into the details. Let's finally get to the first definition of this paper. In this paper, and by the way, we will revise this notion. Okay, in this paper, a state space, omega, is a non-empty, compact, and measurable subspace of the universal state space. That's everything we ask. And if you're wondering, like, okay, wait a second, why is this a new definition? What's so special about this new definition? Well, what is happening in the literature literally all the time is that there is this additional definition. So all the state spaces that you find in the literature, I don't care which paper you pick, I can bet on this, satisfy this property here, which is called belief closure. And here we're using that tau star function. And the idea is the following. Start from a state space. A state space is belief closed if it doesn't matter which agent you pick. It doesn't matter which type of that agent you pick. That type is putting probability, positive probability, only over types that were already in the starting state space. The support of a probability measure is the set of, or closed set of all the elements that get positive probability from a probability measure, okay? Why is this very important for our purposes? Due to this remark that will come back. A type structure always induces a belief closed state space and vice versa, which is the reason why all the state spaces that you find in the literature are belief closed. Okay, enough with recalling stuff. Let's see now the problem. All the machinery I introduced, can this machinery capture misalignment? Because that's the problem. That's the problem we are interested in, okay? Now I'll tell you how to read this picture here, which should somewhat help. But let's fix some notation. Okay, we have once more set of individuals, Anne and Bob. We have once more set of states of nature, theta r, yes, it's going to rain, theta n, no, it's not going to rain. And now we want to use infinite coherent hierarchies of beliefs as types a la Arsani to capture misalignment. The story we said before, right? That mismatch between what Anne believes about Bob's beliefs and what Bob actually believes. How do we do it? We go for a very small type structure, okay? And we just did this. Take set of types, Tr of I and Tn of I, okay? We get corresponding state space. Every dot here is a state of the word, okay? That's the name we gave to the elements of a state space. This is not enough for type structure, we need belief function. This is the belief function. Okay, so type Tr of agent I puts probability 1 on the fact that it is going to rain and the type of the other agent is of type R. type Tn, probability 1 on the fact it's not going to rain, and the type of the other agent is not going to rain. And by the way, how do we read this picture? So every dot, once more, is a state of the word. So take, for example, omega 1. A state of the word is comprised of a state of nature, a type for Anne, and a type for Bob. Now, the arrows means that, for example, blue arrow for Anne means that the type of Anne in this state, TRA, puts probability 1 over the state of nature and the type of Bob that is in omega r. And if we check all the arrows and this definition, everything fits. And by the way, why is this object belief closed? Well, because it's very easy to see. Look at the types here. Look at the states of the word. All the arrows stay within the boundaries. Belief closed. Now, let's see why Harsanyi was a genius. Because Harsanyi was a genius. Harsanyi was a genius for this reason. When I presented you infinite coherent hierarchies of beliefs, you went like, oh my god, this guy's dropping like stars and capital letters like they're candies, but okay, I think I see what's going on. All these Greek letters, I think, okay, you have first order belief, second order belief, and so on and so forth. But how is it possible that from type structures, you get implicitly infinite coherent hierarchies of beliefs? And that's the genius of Harsanyi. Because he didn't have the machinery I told you before, but he had this genius idea. So let's focus, for example, on type TR of Anne. Okay? Now, let's focus on the corresponding definition of the belief function. It's this one, okay? This type TRA puts probability 1 on the fact it's going to rain, and Bob is of type TRB. So, according to Harsanyi's formalism, we also need type TRB. We put it here. And this is the definition of the belief function for this type. We have one theta r and one TRA. Now, let's see how to get the infinite hierarchy of beliefs. Let's start from first order belief. So a first order belief for Anne is, how do we get it? Well, quite simply, let's forget, she has these beliefs here, right? Let's forget the part on Bob, and let's write this little part down here. This is going to be a first order belief, right? Second order belief, and this is the genius. You see, it's blue, blue, okay? Now, second order belief, how do we get it? Well, she has probability 1 over this type, this pair, right? So once more, we put 1 theta r here, we get it. And now it's 1 over TRB. But now look at TRB. First order belief for TRB is 1 theta r, and we put it down here. And the colors are going. So if, for example, we went to the third order types, it was what? 1 theta r, first order belief. 1 theta r, TRB. TRB is 1 theta r, second order belief. Now, 1 theta r, TRB. TRB is 1 theta r, but also 1 TRA. What's the first order belief of TRA? It's 1 theta r. And that would be, and so on and so forth. It's genius. It's absolutely genius. There is a reason if the guy won the Nobel Prize. It's very well deserved, absolutely. But now we have to ask ourselves, do we get misalignment? And that's a problem. Because, you see, I put all this type structure to capture our story. And if we think about our story, the story was, we as outside omniscient observer, we know that Anne believes it's going to rain, and that Anne believes that it's going to rain, and Bob believes it's going to rain, and so on and so forth. This is for Anne. And for Bob, Bob believes it's not going to rain, and Bob believes that it's not going to rain, and Anne believes it's not going to rain, and so on and so forth. So for Bob, it's all about not rain. But here, there is a little bit too much stuff, because the only infinite coherent hierarchies of beliefs as types we care about are actually these, TRA and TNB. The reason why I put the slides before, it was to show that Harsanyi was a genius, of course, but also to sort of make common knowledge in the room how we unpack information from types. You see, in order to unpack the information from TRA, we need TRB. It's part of the machinery. It's literally how it works. But we know that TRB does not actually correspond to anything that is in the head of Bob. It's a byproduct of the machinery. It's a byproduct of the framework. But it's not there. It's not in his head. And it turns out that for Bob, we need TNA. But TNA is not there. We know it's not there. We need it to properly get from T and B the infinite hierarchy of beliefs we care about. So what's the problem with Arsani type structures? Arsani type structures are not capable of distinguishing the red types here, the real types, the real infinite coherent hierarchies of beliefs, from those that are the imaginary ones, the one we need in order for the machinery to work. Let me be a little bit poetic. It's a little bit like what is happening with the critique that Hegel made of Schelling. It's like the night in which all the cows are black. Okay? Under Arsani, all the types are black. We cannot distinguish them. And that's a problem, because we want to distinguish them, because the behavior predictions we get depend on the real ones, should depend only on the real ones, not on the fake ones, not on those that we need for the machinery to work. That's the catch. And that's why type structures indeed fail. That was the spoiler I gave you before. Okay? So let's define misalignment. Because now we introduce all this bunch of stuff. Now we can define misalignment. And this is the definition, which is a monstrosity. Don't try to read it, please. What I want you to do is to agree with me once more on the fact that all the kind of informal definitions I gave you were one and the same. Now, if we agree, I'm going to show you that I'm not cheating. Let me put down here the very last version. And let's go now step by step, and we will see that here nobody's cheating. Okay? We have a set of agents. We have a domain of uncertainty. We had a model of the interactive beliefs, but now we know how to capture model of interactive beliefs. That's a state space. I mean, half an hour talking about that kind of stuff. Now the model presents misalignment. Well, the state space is misaligned if there exists an agent I that holds beliefs regarding an agent J's beliefs. Okay, now, this is an hierarchy function. Plug a type as an infinite coherent hierarchy of beliefs, and we get this. Okay, but we will get into these details. What is important here is the following. First of all, in order to capture the beliefs of an agent regarding anything, we use a type. Here there is a type for this agent I. Notice, we don't care about number one. Why we don't care about number one? Because we don't care about the beliefs of that type over the weather in Paris. This is not what misalignment is all about. Misalignment is not about the beliefs of a given agent concerning the states of nature. Misalignment is about wrong beliefs concerning the beliefs of somebody else or higher order beliefs. So every natural number can work with the exception of number one. Because with number one, we would get the first order beliefs of an agent. The first order beliefs are on the states of nature. And finally, and then we have this monstrosity here. I'll show you how to read this, that are not actually held by J. And here we have this projection function. Remember, universal type space was a product object. You take the projection, you can do it. Okay, funnily enough, first of all, where lies the problem? The problem lies here. Okay, the problem lies in the fact there is a mismatch between what Anne believes regarding m-1 beliefs of J and what actually J has in his head. How do we see this? Funnily enough, we see this with this object. And it sounds completely ridiculous, but hopefully I will convince you that this can be useful. So first of all, let me clarify. What we have here is literally what is in the head of agent I regarding agent J's m-1 beliefs. What is happening under misalignment is that what we get here is not included in what is actually in the head of agent J. This mismatch. That's how we capture misalignment. Now, what is going on here? The problem lies here. We start from a state space. This is the blue part. Notice this hook arrow means, by the way, all these arrows are nothing more than a way to capture functions, okay? So for example, here there is this function that maps from Ti to this object here, okay? And then we have another, we take the marginal and we get here. Okay, now we focus, under misalignment, we have that for agent I, we can have this m, we can find this natural number such that when we take the hierarchy function and then we go like, hey, wait a second, I don't care about all the beliefs of agent I over all this kind of stuff. No, we just care about agent J. Okay, we get here. Now, big question, why do we use the support? This is crucial. Let me clarify this. The idea is the following. little variation on our example. Let's consider the case in which Anne believes that it is going to rain in Paris tomorrow, first order belief, but now second order beliefs. She believes it's going to rain in Paris tomorrow, and with probability 1/3 that Bob believes it's going to rain, and with probability 2/3 that Bob believes it is not going to rain. The thing is, for misalignment, we do not really care about the 1/3 and the 2/3. We just care about the fact that Anne is conceiving these two options. And so we use the support to say, hey, you know what? 1/3, 2/3, I don't care. Just give me the corresponding beliefs. That's why we use the support. Now we go back, and now we are here. The problem now, and this is where the definition, this monstrosity comes in. The problem now here is the following, and naturally we should go back here. But we don't. And that's the problem. What is happening is that when we keep on moving from agent I, basically there is a mismatch. When we try to get what agent I believes about agent J, and we try to go back to the original state space, we do not go there. We go to the universal state space. Of course we go to the universal state space, everything is there, but we do not go to the original state space. And now if you're thinking like, come on man, this is ridiculous, this is a nightmare, no human being is going to use it, you know what, I agree with you, by the way. But, first of all, this provides a definition which is based on objects out of which everything can be elicited. So this is absolutely crucial. We are not using labels or stuff like types. We are using infinite hierarchies of coherent beliefs, stuff that can be elicited, first thing, okay? And second thing, well, it works. Let me show you that it works. First of all, if you are interested in misalignment, now you're not interested anymore in this big state space. You're just interested in the real types, the red types. And these are the only two states that contain the red types. Look, omega 1 is the only state which contains, in which both types are the red ones. And omega 2 is the only one in which you have, those are the only states in which, in both cases, you have red types. So this is the original state space you are interested in. So we have literally one type for one agent and one type for another agent. Now, this is another way of writing what we keep on write down. First order belief of Anne, she believes it's going to rain. Second order belief, she believes it's going to rain, and Bob believes it's going to rain. But now, let's go to Bob, and the only type of Bob. Focus on the corresponding first order belief. Let's plug it here. Bob believes it is not going to rain, but here there is the catch. Take the monstrosity here. Plug the type TRA of Anne. This is Anne's belief on Bob's first order belief. But this is, of course, not included in this, which is Bob's first order belief. And this was the original definition I gave before. It's terrible. No human being is going to use it, but it works. So the problem now is, okay, wait a second. Thanks a lot. What am I going to do with this? Because it's a nightmare to check for misalignment. Can you characterize it? Can you operationalize it? And that's what we achieve. And this is very neat. This is the characterization. A state space is misaligned if and only if it is non-belief closed. Okay? And before commenting on the result, let me show you how ridiculously easy it becomes to check if a state space is misaligned. Remember, at some point I told you, well, you know, a state space, that old state space, that was belief closed. Why? Because all the arrows were inside the boundaries. But now look here, the boundaries are these, and all the arrows are out. That's non-belief closed. So this is, in a sense, interesting per se, because it's literally the very first time that non-belief closed state spaces take central stage in the literature. It was never before. They existed because we cared about belief closed state space, and they were just like, oh, they are the things we are not interested in. So if the focus of this paper was on interactive epistemology, it was in a sense interesting per se as a result. Turns out that once more we are interested in the social scientific phenomenon at large. Okay, so now what are we going to do with this? Because now we want to get the behavioral predictions. Okay, well, so by the way, we answered to the second bullet, mission accomplished, and we also characterize it, non-belief closed state space, thumbs up. Let's proceed. How do we develop a framework to capture the behavioral predictions under misalignment? Well, we need a little bit of an intermezzo, because we need to see how, and this is the problem with this paper, we need to see all the kind of problems that there are in the literature to see why we need to go through all these trials and tribulations. It's terrible, but it is what it is. The intermezzo is the following. We should ask ourselves, what do we do when we do interactive epistemology, when we have all these state spaces? What do we do? Well, roughly this is what we do, okay? Very quickly. It's these 3 steps. So first of all, we have a bunch of agents, we have a domain of uncertainty. First thing we do when we have set of agents and domain of uncertainty, we get to the corresponding universal state space. Okay, now let's imagine that we are in the lab. We are eliciting beliefs for every agent. We get some hierarchies. So we build a corresponding state space. Okay, very nice. Now here, these white dots, big dots, are a way to capture the idea that the state space is non-belief closed, because now we are contemplating the possibility that the state space is non-belief closed. Okay, so far so good. But there is one thing I didn't tell you when I was talking about non-belief closed state spaces. Namely that you cannot do anything with them. I mean, there's like literally the machinery we have doesn't allow us to work with non-belief closed state spaces. We just cannot do anything. So we need to make these non-belief closed state spaces belief closed. How do we do it? Well, it's easy. The missing types, put them in the pot. And that's it, right? But there is a 4th step. The 4th step is that when we do interactive epistemology, we also put some assumptions of interest. Let's put assumptions of interest. And now if I ask you, oh, wait a second, which is the very last part, okay? So now if I ask you, oh, wait, what are the states you started with that correspond to hierarchies you are interested in that are also compatible with the assumptions of interest? And I ask you this. Well, maybe you're going to go like, oops, you clicked a little bit too fast. Because now, once more, all the cows are black. How do we know what are the states we started with from those we created in order to get a belief closed state space? And so the problem is that we want to find a way which is not too naive to start from objects that are possibly non-belief closed, to make them belief closed so that we can get behavioral predictions. Okay, how do we do it? A framework for misalignment, and very quickly, agent-dependent type structure, that's the idea. So if we contemplate the possibility of misalignment, we have to accept the idea that we have to deal with non-belief closed state spaces, okay? So we start from a state space of interest, okay? If it is non-belief closed, we know now via the characterization it is misaligned. How are we going to proceed? We cannot just pick, the missing types, okay? Because all the cows are black. So we cannot do it. How do we do it? And we introduce this framework, okay, which basically we work as follows. We pick an agent I, we pick the corresponding set of types, okay, and we build around this set of types as infinite current hierarchical beliefs, we build a type structure. We call this type structure agent-dependent type structure. But this is a type structure in its own right. The only property that this type structure has to satisfy is that it has to contain all the types you started with for that agent. And that's it. So what does an agent-dependent type structure capture? Basically, it captures what is floating in the head of one specific agent. And now we do this for every possible agent. So when we focus and we contemplate the possibility of misalignment, it's not anymore like, oh, one type structure fits them all. No. We take the agents, and for every possible agent, we build type structure, okay, agent-dependent type structure. Each and every agent-dependent type structure captures what is floating in the head of one specific agent. And if we're thinking, come on, this is absolutely crazy, well, think about those people there. They're driving. They have some beliefs regarding the other people that are driving in the opposite direction. It's not that they are sharing these beliefs, they are living in their own little heads. And everybody's living in their own little heads. And if you find this a little bit too poetic, think about the lab. In the lab, the subjects are in their own little cubicles with their own little hierarchies of beliefs floating in their own head. And maybe somebody now could go like, okay, whatever, but still, I mean, this is madness. Okay, I hope to convince you now that, as in the words of Polonius, though this be madness, yet there is method in it. Okay, so what's the method? Hopefully I will convey where the method lies. The method is the following. Okay, we get a taxonomy. And this is going to shed lights on very many things. So once more, fix the state space, consider a profile of age-independent type structures. Now recall the remark I dropped at the very beginning. Every type structure induces a belief closed state space and vice versa. An age-independent type structure is nothing more than a type structure in its own right. So we get a belief closed state space. Now get all these agent-dependent state spaces, we get these definitions. So you have this profile of agent-dependent type structures with corresponding agent-dependent state spaces. We say that this profile is degenerate if basically starting from the state space you started with, you're not going to add any new states. Otherwise, not degenerate. Common if pick all these kind of states, make pairwise comparison, they are all one and the same. Otherwise, they are non-common. Okay? Why is this relevant? Because we get this. Okay? We get this matrix. And it turns out that we get this taxonomy. So it turns out, okay, this is not possible, literally. But it turns out that what we always studied in the literature is here. Those are the standard state spaces we always studied in the literature. But we never contemplated this entry here or this entry here. So now we can basically get into the details of what a state space is and what's inside, so that maybe we can get novel behavior predictions. Before going there, let me quickly show you how we can build agent-dependent type structures for Anne and Bob in this case. This is a very spatial agent-dependent type structure. We call it the minimal one, not getting into the details. But we are starting from TRA. Well, in order to get an agent-dependent type structure for Anne, just add TRB, and everything is here. And for Bob, you start from TNB, put TNA, and we get here. As a matter of fact, let me put some colors. This is the agent-dependent state space, the singleton for Anne, and this is the agent-dependent state space for Bob. As a matter of fact, in this case, it's pretty obvious that this profile is non-degenerate because we are getting new states with respect to those we started with. And it's non-common because Anne is living in her own little world and Bob is living in his own little world. That's the idea. Okay? And by the way, this idea of one is living in Anne is living in her own little world, Bob is living in his own little world. Think about people driving. Okay, game theorists like examples with cars. I don't know why. But think about people driving. Okay, let's imagine I'm driving, and I believe that in Paris people drive on the right. I also believe that Mickey believed that people drive on the right, and so on and so forth. So for me, between me and Mickey, it's all about driving on the right. God knows, actually, Mickey believes that it's normal to drive on the left. By the way, I hope you're not driving. And here, in his own little head, Mickey believes that everything is on the left, on the contrary. That's what I mean. That's what I mean by everybody's living in his own little head. Now, what do we get out of it? Okay, we developed now a framework. We want to get behavioral predictions. And misalignment matters. So I think one cool thing when we go back addressing like old problems, and with the idea of developing some new machinery, new lenses, is that we have the possibility to go back to tackle some old issues and see if we can get some better, but some new understanding on some old phenomena. So now we will tackle, what we tackle in the paper is an old established result in microtheory, which is Marx's theorem, okay? This is not the Marx I had in mind, I'm sorry. I didn't have in mind actually Karl Marx, I had in mind Groucho Marx. Yes, and I think that by now it's clear that I'm referring to the so-called no speculative trade theorem by Milgram and Stokey, 1982 theorem 1. It was called the Groucho Marx theorem because Groucho, as literally it was called, check the paper, Groucho very famously stated, I'll never join any club that would have me as one of their members, okay? And this is the statement of Milgram and Stokey. This is a very informal statement. What we care about, okay, is a very general statement. it's a very general result, sorry. What we care about is the fact that they need a common prior, and at some point they use this common knowledge operator, okay? And bottom line is that basically receiving private information given certain assumptions cannot create any incentive to trade, okay? This is why basically it's called the Groucho-Marx theorem. Well, as soon as somebody goes like, oh, I would like to trade, everybody's going like, no, then I don't want to trade. That's the idea. Now, no speculative trade, right? Well, that is what we know until now. Because now, well, it depends. It depends. Because contemplating the presence of misalignment leads to novel behavior predictions, and that's the catch. Okay? Because, first of all, from Milgram and Stokes, theorem 1, under appropriate assumptions such as common prior, we have no speculative trade. And they also use this common knowledge operator. Now, in the literature, we don't use the common knowledge operator anymore because knowledge is very strong. Now we use common belief. Okay? Under common knowledge, you cannot be wrong, basically. Okay? But belief, yes. You can believe something with probability 1 and be utterly wrong, okay? And that's why we use this in the literature. Now, what is happening is that appropriately defining the common prior along with corresponding assumptions and needed modal operators such as belief and common belief, as I was saying, in the context of age-independent abstractions, under misalignment. Once more, we have this matrix here. This is not possible. Those are the standard state spaces. What do we get in terms of speculative trade? This is what we get. Of course, we get Milgram and Stokes here, because this was the case of standard state spaces, of course. And Milgram and Stokes is about standard state spaces. But here, we have an extension of Milgram and Stokes. Here, we get speculative trade. So contemplating the presence of misalignment allows us to get a more fine-grained view of state spaces and corresponding behavior predictions, okay? So, let's wrap up. What did we do today? So we introduced the elistable notion of misalignment. We characterized it via non-belief closed state spaces. We introduced a framework to keep track of misalignment. We showed that taking into account misalignment, we obtain a more fine-grained taxonomy of state spaces. And we described a context where misalignment matters. Speculative trade. What else do we do in the paper? We provide a foundation to age-independent type structures. I drop at some point during the presentation that we deal with what are called minimal age-independent type structures. We basically build a minimal age-independent type structure from the ground up with a mathematical procedure. We define modal operators of interest, and we formalize the notion of common prior under misalignment. Now, take-home message, 3 take-home message. First one, beliefs and beliefs about beliefs and so on are in our heads. They are. We can elicit them. We can do whatever we want. But at the end of the day, they are in our heads. Second one, we talk about state spaces. We talk about common prior. We talk about common belief, iteration of beliefs. But now, by contemplating misalignment, we should ask ourselves, what do we mean exactly? What does it mean to say exactly, it's commonly believed? Think about the example between me and Michi driving on the right or on the left. I can think it is commonly believed between me and Michi that in Paris you drive on the right, and Michi can believe that it is commonly believed between the two of us that in Paris you drive on the left. Finally, taking into account misalignment, we can perform an analysis that is sensitive to the 2 points just made. Now, bottom line, and maybe this is going to sound mysterious, there's certain kind of analysis which you do not really need type structures. You just need infinite hierarchies of beliefs as such. In that case, misalignment doesn't play any role. But as long as your analysis does depend on the actual state space you are picking, then misalignment plays a role. Okay? So, that's the bibliography. Let me thank Olivier, Stefano once more, all of you for being here, for your attention, for having bear with me during this madness. I hope that I showed you that there is method in it. And yeah, let me thank you once more and shut up.
Yeah, two things. And first, that so you set up, so you finally basically you claim that whenever there's there's a trade, then people have to have the different belief. So that is the same message as previous literature sent. You just have the different state space, but essentially you still claim.
No, but now the problem becomes like, what is the state space? And to properly address all the operators and the common prior. And now the thing is that the kind of assumptions that they have there, now you have to translate them in this new context. Because once more, we should ask ourselves, what do we mean when we talk about common prior? I mean, it's a similar issue, for example, is in the literature on unawareness, in which over there they have the issue in terms of, okay, how do we deal with the common prior, with this lattice of state spaces, as what Martin, with Heifetz, Burkhardt and Martin do. And in a sense, once more, the problem is, okay, how do you deal with these objects in this new setting? And this is pretty much what is happening here, because we have to deal with now these new objects, and you basically have the same statement under this new light, but now you have speculative trade. And by the way, let me point out something. We also have a paper which is on game theory and the kind of behavior predictions that you get in game theory. Okay? And there, for example, we focus on what is called rationality and common strong belief in rationality. And there is, once more, this is a solution concept that does depend very much on the state space you start with. I always say, half jokingly, if you're interested in this paper, don't read it, because very soon it's going to be, we are going to write a new version. But the main intuition there is the same, and you get novel behavior predictions once you take into account misalignment, and there you don't even have issues in terms of what is the common prior and so on and so forth. It's literally the fact that you are taking into account these agent-dependent type structures, and you have to ask yourself, okay, what does it mean, rationality, common strong belief in rationality, when everything works now at the, so to speak, micro level of the single agents?
Well, then the second thing is that you have this agent-based state space. So how about you have the product of all these agent-based state to consist of universal state space? So it's different from that.
I'm not sure I see the question. So what we are saying is, correct me if I'm wrong, so we have these profiles of agent-dependent state spaces that are derived from the agent-dependent abstraction. And what you're saying is like, okay, take a product, okay. I'm not sure I see why we need to take a product. Okay, but okay, we take the profile. And what about the universal object?
Then you will have the more universal state space.
But do you? I mean, those are almost incommensurable. Like they're like in a sense different objects. Everything is living inside the original universal state space you started with. So, I mean, every single projection, of course. But then what you're getting is like, and yeah, I'm not even sure. But yeah, no, cool. Thanks anyway.
Perhaps just to clear my mind about what you're doing. To some extent, Arseni's type are deeply correlated with the idea of equilibrium. And you're moving us toward this object, which could be a speculative equilibrium. Is that what you have in mind with misalignment, being able to model some situation where people succeed in coordinating on some course of actions without having common knowledge?
So, no, first of all, thanks a lot for the question. Yes, well, I would say that this work here is, it's in a sense more basic, right? But we are completely correct when you say that typically we use types, well, a certain branch of game theory in order to deal with games with incomplete information, and we have, the second Arsenic transformation, Bayesian Nash equilibrium, and so on and so forth. But there is also, a branch of literature in which type structures are used for other purposes. So, for example, when I was referring to interactive epistemology, I was, for example, thinking about epistemic game theory. But now, going back maybe more to your question, in a sense, by passing game theory, what we want to deliver here is that, yes, we are assuming, what is happening when we work with one type structure is that we are assuming a lot of stuff there. We are assuming that so to speak, everything is pooled inside this type structure, and all the beliefs are inside, and everybody is kind of agreeing that the beliefs are going to be there. And okay, fair enough. But at the same time, there is the possibility that we can live in different worlds. And it would be interesting to see, okay, what are the behavior predictions we get? Of course, the goal is not to say, anything goes, whatever. But in a sense, what we try to show, and also in the other paper, the one on game theory, what we try to show is not that you get whatever. As a matter of fact, you can get some type behavior predictions from an epistemic game theoretical standpoint in that case. And this comes from contemplating the fact that agents, once more, we live in our own little worlds. I mean, it's beautiful, of course, to say, yes, we're in a cubicle, every subject is in their own cubicles, and all these beliefs are pulled together. Let's just use one type structure, it's going to make the job. Yeah, of course, it's very handy. But I think that, for example, this is also related. I go back a little bit to unawareness, okay? The fact that unawareness, so one magical thing that happens when you get into arsenic type structure is that you realize that it's really a genius idea. You can do everything, literally everything with it. That doesn't mean, though, that they are always fitting perfectly the story you want to catch. So, for example, all this literature on unawareness, in a sense, makes the point, hey, look, yeah, sure, you can do everything with arsenic type structure. It's a very well-deserved Nobel Prize, absolutely. The more I study this kind of stuff, the more I think it was genius. But that doesn't mean that, you can tweak things around as much as you want, and then maybe, in some way you're going to capture this unawareness story you want to capture. But that is tweaking, big time. While with an unawareness model, you get it right away. Yes, of course, the notation maybe is heavier. We need to get accustomed, of course, to this literature, this notation, but that's how it works, for example, there. And here it's, in a sense, the following. Yeah, maybe there is a way, even if in a sense, I think that pretty much as in the spirit of unawareness, we try to point out that, yes, all the cows are black at some point under Arsani. But yeah, maybe there is a way in which you can tweak things, whatever, but why don't we go for the natural thing, which fits the story? Much more naturally, so to speak. So I think there is and hopefully there is also in general this shift, right, in the focus.
Yep. I mean, you take this agent-specific type structure to be basically the smallest belief closed space that contains that agent's types, right?
Yeah.
But the agent knows what the type is. So shouldn't there really be for each type of an agent the belief closed subspace? Because in some sense, different types of myself only exists because I want to think about what other people think about me. But they are not real. They are not in my head in that sense.
I see what you're saying.
So if you there's a more solipsistic version.
Yeah, it can get even worse. No, but I think I see. Yeah, but then, right. So I think there are two sides here of the story. One thing, which, by the way, we write in the paper, and I think it's very interesting, right? We in a sense, we like to think about the fact that types, infinite coherent hierarchies of beliefs are a way of capturing interactions and so on and so forth. And then we go we could use this kind of stuff, for example, in the lab. But for example, when we are in the lab, right? I mean, when you elicit an infinite hierarchy of beliefs, first of all, it's not infinite. It's never infinite because you're going to stop to elicit at some point because you are running out of money also and of time. But you're going to elicit just one. Up to a certain point, just one. Okay, so maybe this is kind of fitting, in a sense, with the way in which we were telling the story. And now going back to what you were saying, there could be maybe some robustness concern. Is when you go okay, yeah, let's pull some of them. But I see what you're saying. But you could go I don't know. I have to think a little bit about this. But I see the point. But if you take, for example, the union there, should it be a problem?
No, but I mean the point is different types of myself they're not necessarily in my head. I have a certain belief about the world.
That's true. But
that considers that you believe certain things about me that regards me to earth sometimes.
That's true.
But usually not all of them.
That's true. But then in a sense, part of, and this is also the reason why we are very explicit, it's a way of, that's why we say, look, take the perspective of an outside omniscient observer. This outside omniscient observer say like, yeah, pull these types, contemplate, like, look, I don't really know which type is Mihi, but I'm contemplating these two types as infinite hierarchies of Bliss for Mihi. Who knows which one is not? But no, but I see what you're saying, yes. Excellent.